you still have to give it a try. You still have to try to approach your teacher with whatever. Otherwise, they can't do much. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 22. Okay, I cracked 20. Let's see. Can you make sure that, yeah. All right, cool. So, did everybody get this from last time? Anybody still need this handout about sequences? Everybody's got that? Okay. I think we pretty much finished this. If I remember correctly. We didn't really do this one though, did we? We just sort of talked about it for a moment. So, if you weren't here last time, that's a really good video to watch. We're not quite done with section 11.1, so if you try to start doing the homework, some of it might not make immediate sense. So, just always try to do as much as you can. We're going to finish up 11.1 tonight, start talking about 11.2 a little bit. Yeah, make sure that door closes. It's having an issue. Yeah, thanks, man. Okay. So, anybody have any questions from anything? Homework, general class stuff? Any questions about anything? Okay. All right. Let me do this before I forget. That guy going. Okay. A little less glare. Let's look at this guy right here. If you were not here last time, oh boy. Let's do this. Let's review a little bit. Okay. So we have kind of two separate ideas. We have sequences, which all of you have worked with to some degree. You've seen sequences before. The first one I did was 1, 4, 7, 10, and I said, what's the next number? And you guys very quickly said 13, because 1, 4, 7, 10, the sequence is I keep adding to. Yes? The less I give you, the more possible sequences it could be. And very often, I'll give you what I think is enough, but somebody else will come up with something I didn't think of, and I'm like, oh yeah, that works too. You guys at all with me? So some of those questions, there might be more than one answer possible if I don't give you enough information. Okay, we'll stop there for a second. We did an example like 1, 2. It could be 1, 2, 3, 4, 5. It could be 1, 2, 4, 8, right? You guys see what I'm saying? So, I've got some notation. I can either use a set of brackets to indicate a sequence. I could use this notation to indicate a sequence. So last time we developed the formula for that sequence. 1 plus so many 3's to create that sequence, yes? Do you guys remember that? So this, I can't remember the book uses this terminology, but do you guys remember what I called that? Starts with a G. Generating. It's the generating function. Not a huge deal, because I don't even think the book calls it that, but does that make sense? It's the function that generates the elements of the sequence. So I like that name, it kind of makes sense. Okay, so you have a bunch of little generators running around, not really powering anything, but they're creating numbers, which is neat. So is everybody with me so far? So that AN notation is like function notation. If I want to know, let's just double check. If I plug a 4 in, I should get the 4th element. And what is this if I plug a 4 in? That's 3 times 3 is 9, plus 1 is 10, which is exactly what the 4th element is. If I plug a 5 in, I get Lilu. I get Big Bada Boom. No? You guys ever seen the movie The Fifth Element? If I plug in 87, I will get the 87th element, which is much quicker than writing this out until I get to the 87th element, yes? So that is the immediate usefulness of being able to find this kind of closed form of this sequence. Okay. Is it always easy to find this? Hell no. Right. So we did some examples. What about if I had this sequence here? That'd be nice and not reduce. So what I would want from you is a form for AN. And the smartest thing you can do, and you're going to see exactly this in the homework. They're going to give you, not exactly this problem, but exactly this kind of problem. What I highly recommend you do, you can see already some simple stuff. Can't you see both top and bottom? Can't you see kind of what's going on, the pattern? But to really identify it for yourself, put A1 is 2/5. How do I go from A1 to A2? What do I do? What do I do to A1 to get to A2? Yeah, multiply the top by 2. Plus 1 on the bottom. Yes? How do I get to A3?
3 2s.
And on the bottom?
Plus 2.
Yes. So this is 2 times no 2's over 5 plus no 1's. This is 2 times 2 to the first over 5 plus 1 1. This is 2 times 2 squared over 5 plus 2 1's. Okay, let me stop for a minute. I did that a little fast, I'm sorry. Do you see what I'm trying to find? If I'm trying to create a function where n will generate that element, I want to look at each element and figure out, well, what piece of that form is changing? That's where I'm going to put n, yes? So can anyone see, what's a better way to write? There's even one more thing. What is 2 times 2 to the 0? 2 to the...
N minus 1.
No, I'm sorry. Just 2 times 2 to the 0. It's 2 to the first, yes?
Yeah.
So this is 2 squared, yes? And this is 2 cubed, yes? Okay, good. So if A1 is 2 to the first, A2 is 2 squared on top, A3 is 2 cubed on top, what is AN?
2 N.
Alright, do you guys see that? Do you see how that can get very complicated very quickly? This is a relatively easy sequence. And on the bottom, what do we see? 5 plus A1, this is 0 1's added to 5. A2, this is 1 1 added to 5. A3, this is 2 1's added to 5. AN, A1 is 0, A2 is 1, A3 is 2. N minus 1 times 1, yes?
Yeah.
Is that okay? So then I end up, just to kind of write this, I end up with 2 to the n over 5 plus n minus 1, which is 2 to the n over 4 plus n. How do you check it? What should the third term be? 8 over 7. What do I get when I put a 3 in? 2 cubed is 8. 4 plus 3 is? So that kicks out. So you can very quickly check what you've done. Okay. You can tell how those are very often some of the harder problems. And just to let you know, they will be those slightly more harder problems, and that's why you should really do it very systematically. Okay, maybe. Okay. Now, once I have a sequence established, once I'm looking at a sequence, there's a question I can ask, because what did I imply when I wrote the very first sequence I wrote? What did I imply by that? Goes on forever. We will go on forever. So would this sequence, I'm sorry?
I said dot.
So would this sequence converge? Why not? What does converge mean?
It goes to a specific number.
Yeah, it's approaching a finite number. Like, would it make sense for me to say the last number in the sequence?
No,
No, because the sequence goes forever.
right.
But you can sort of say colloquially, the last number in the sequence is a finite number, right? So this one is not convergent because the last number in the sequence, there isn't one, it just goes to infinity, yes? You guys kind of with me? We could develop a sequence very easily that is convergent. In fact, the easiest, dumbest one would be 1, 1, 1, 1, 1, 1. Okay, is that convergent?
Yes.
Yeah, it never freaking stays away from 1. It's always 1, yes? It eventually gets eternally close to some number. It's always 0 away from 1. Okay. So the idea of a limit is at some point you are as close to a certain number forever as anyone could ask. So if the element, if I had a sequence, here, let's do a specific example of this. 2 minus 1 over n. Can anyone tell me why this is convergent?
Because
What do you take to investigate whether something's convergent, a sequence is
The
convergent or not? What do you take? You take an Advil. No.
the limit.
You take the limit. I love it. And can you guys see the limit as n goes to infinity would be 2. Here. Well, it'd be 0 for this piece. So what's the limit of the whole thing?
2.
2 minus 0, 2. Yes?
Yeah.
All right. Which means if the limit is 2, at some point the elements have to forever be as close to 2 as I want it to be. If somebody said, I want you to be 1/10 away from 2, at least that close forever. Can you guys see very easily how I can get that close? Okay, let me see. What n makes an 1/10 away from 2? You can see it on this one. This one's nice. Yes, maybe? Real quick. What do you get when n is 2? What's a2? 2 minus,
2 minus 1/2.
which is 1.5, 1.5. How far away from 2 are you? A half away from 2, yes. How far do you have to go until you're 1/10 away from 2? N equals 10. If you're at n equals 11, are you closer or farther away from 2? Because I'm subtracting less, yes? In fact, forever after 10, aren't I always closer than 1/10 away from 2? If somebody said, okay, sequence boy or girl, I want you to be closer than 100th forever. I want you to always be closer than 100th from 2. Well, we just go how far out? 100th. Let's go out to n equals 100. Forever after n equals 100. Do you all agree that the elements would be closer than 100th from 2? A 100 is 100th away from 2, yes? A 101 would be 1 over 101 away from 2, which is closer to 2. Are you guys with me? So the idea of a limit is that eventually you are as close to that limit forever as anyone arbitrarily wants you to be. So somebody said, okay, I want you to be 1/1000th away from 2. Well, then we just go out to n equal 1,000,000,000. Okay, there you go. I'm always closer than 1,000,000,000. Could I do that forever? Can I do that forever?
Yes.
Could somebody tell me that they want me to be 1 trillion to the trillionth power away? Yeah. We just pick a trillion to the trillionth power for n. Are you guys with me? The formal idea of limit is that at some time, whatever the freak your function is doing, at some time it's got to settle down and stay within so far away from that. Forever. No matter what this within number is. If the limit was actually this, and I thought it was this, and somebody said be this close, I'm like, oh shit, I can't. Well, then that's not the limit. Okay. I'll formalize that here in a little bit, but I just wanted to talk about that real quick. So, looking back at this, how can you tell if this is convergent or divergent? Let me write this down.
Well, it's gonna be an indeterminate form, right?
And is it?
Yes.
Okay, how do you know? What do you do? Well, here I'm gonna take the limit.
Well, it would
Right.
be infinity over infinity.
Totally. It's infinity over infinity, correct?
So you have to use.
So I want to really make this distinction because I made a big deal out of you can't plug infinity in, but I can see what form it's in. That is in the form infinity over infinity. That's not me plugging infinity in, that's the form that ratio takes on. Okay. So what the hell do I do? Can I do like we did before and talk about the degrees?
Mm-mm.
No. So we talked about this a little bit last time, this specific problem. What helps me? Who was it that helped
The
me?
French Medical Center.
French
do.
medical person. Yes. Every time somebody says it, he turns over in his grave and it's like, what was he creeping out? His ashes kind of like rumble around. So how does L'Hopital's work? Is this a ratio?
Yeah.
Is it an indeterminate form?
Yes.
L'Hopital's works. L'Hopital's basically says, and this is when you were doing limits, we always talk about how quickly they go there. So like if I have n squared, real quick, if I have n squared plus 1 over n cubed minus 7, does anyone see why that limit is easy? Don't even write this down, just talk to me.
Just divide.
Why is that limit easy?
Just divide
No,
all of it by
even easier than that.
n cubed.
What's the highest power? On the bottom, yes?
Yeah.
Doesn't the top go to infinity? And the bottom goes to infinity. But who goes to infinity faster?
Bottom.
The minute I say faster, what calculus ideas does that involve? Faster. Faster. Starts with a D.
Derivative.
Derivative, yeah. Isn't derivative all about the rate of change? Yes? So L'Hopital's kind of has an intuitive sense to it. I want to know, does the top or the bottom get to where it's going faster? So of course L'Hopital just said, all right, let's take a frickin' derivative. Now of course there was a big proof to it and so forth, but the intuitive baseline, let me look at the derivatives to help me figure out where this thing is going. Yes? So, unfortunately, we don't have this problem. That would have been easy. Too bad. We have this problem. So now we're gonna have let me go this way. So what I almost always do for myself is I tell myself what the hell I'm doing. I'm doing L'Hopital's now. Please, dear God, don't do quotient rule. L'Hopital's is not quotient rule. How do I do L'Hopital's rule?
You take the derivative of
The top, good,
the
like
top
it's a known
and
function.
the derivative of the bottom.
I love it. So what's the derivative of natural log of stuff?
1 over stuff.
1 over
times
stuff? No,
Derivative.
times derivative of stuff. Is that cool? I could put that up top. And then what's the derivative of the bottom?
1/3 negative 2/3.
And real quick, just to make sure everybody hears this. If you took me for 180, you know this. But this is a silly little thing, but it happens often enough. It's a good thing to know. If I want to do a fraction minus 1, I just do 1 minus 3 over 3. 1 minus 3 is negative 2 over 3. That kicks so much ass when you got like n to the 18/15s. You're like, what the shit? And you're like, okay, 18 minus 15 is 3 over 15. Bam, yes? Okay. Now comes everybody's favorite. You have to simplify that now, right?
Yay.
So, can anyone see something? Let me rewrite this a little bit. Can't all of this stuff get reciprocated up top? Yes? Is that cool? So I'm going to multiply by 3, n to the,
Into the 2/3.
yeah, positive 2/3, yes. So this is where a lot of calculus students kind of lose it. You pick up on the calculus, but then you forget the basic algebraic manipulation, yeah? So if I've got something divided by something, I just multiply by the reciprocal at the bottom. Yeah, so then I can make 6n to the what that's going to be on top?
N. It's just gonna be 1.
That's n to the first times n to the 2/3. What do you do with powers when you multiply like bases? Add them? Yes, I thought you were trying to ward me off.
Oh,
This doesn't work for
Oh.
calc teachers, I'm sorry.
so.
Garlic doesn't,
5
definitely
thirds.
doesn't. I love garlic. Huh?
5/3.
Yes, yes, and again, so here's what's cool. If you want to add 1 to a fraction, you do 2 plus 3 over 3, 5/3. Now, can you see which degree is higher, the top or the bottom? Because that's the whole question here. Which degree is higher, the top or the bottom? Bottom degree is higher. You guys see that? 5/3 is less than 2. So then what's this limit? The bottom grows faster.
0.
0. Could I do L'Hopital's again?
You could,
Because it's still what?
because it's still infinity over infinity.
It's still indeterminate form, yes? You guys see that? But dear God, if it's not indeterminate, L'Hopital's like, you can do me, I have no idea if it's going to be true, right? L'Hopital's only remains true if you start with indeterminate form. I could do L'Hopital's until I go slightly insane. I really don't want to. I'd rather just get the freaking answer now, because now this is just a ratio of two things. I can see the degree is higher on the bottom. I'm done. Yes? Equals 0. Yeah. Okay. And just to kind of tell you, natural log is one of the slowest growing functions. Almost always, if it's up top, the bottom is going to overwhelm it. If it's on the bottom, the top's going to overwhelm it. Don't try to get the answer straight from that, but you'll see as you do some of these. Natural log is like one of the slowest growing functions there is. I'll get there someday. Right? X squared is like, bye. Alright, sorry. Okay. So we finished this. By the way, the other side, don't worry about. I might try to talk about this a little bit, because it's really good to know, and it does come up in this chapter. We'll see. Okay. But hold on to that in case I try to come back to that. Okay. So I want to finish up section 11.1. And just to kind of remind you where we're headed, 11.1 sets up the real foundation of things. We have a list of numbers separated with commas. That's a sequence, yes? A sequence doesn't necessarily have to have a generating function, to be honest. A sequence could be all the digits of pi. So it'd be 3, 1, 4, 1, yes? You guys kind of with me? It would be all in the, is there a generating function for that? No. You guys see what I'm saying? A sequence could be the number of letters in the last name of each student as you're seated. So I can make a sequence of numbers based on the letters in your last name. Is there a generating function for that? No. Most of the ones we're going to look at and work with, thankfully, do have generating functions. So then I can do stuff like limits to them. Okay. I like it. Cool. So 11.2, we're going to finish up 11.1. 11.2 is going to really build the foundation for the whole chapter. So 11.2 is where we're going to start taking all the elements of a given sequence and adding them together. And we've already discussed how that answer can come out to be something other than infinity. You guys remember that? 0.1 plus 0.01 plus 0.001, that is a sequence. And if I add them all up, I get 0.111111, which is definitely less than infinity. So that's going to be the whole driving thing for this whole chapter. But I can't do series until we really understand sequences, because series are just adding up sequences. Okay, so let's finish up 11.1. Oh shit. I wrote some notes while I had glasses, so I can't read them unless I have glasses. Okay. First thing I want to do is kind of like formalize what I was talking about earlier about you can get arbitrarily close to something if it really is the limit. So let me say it like this. The limit as n goes to infinity of an is L. Ooh, if and only if. Have you guys ever seen, let me stop right there. Have you guys ever seen if? Have you guys ever seen if and only if? So if I say, if it rains today, I'm going to bring my umbrella. The rain causes me to bring the umbrella. Yes? If and only if would be both ways. If it's a four-sided figure, then it's a quadrilateral. Yes? If it's a quadrilateral, then it's a four-sided figure. Yes? Doesn't that work both ways? So then I can say it's a quadrilateral if and only if it's got four sides. If and only if just means it works both ways. Does that make sense? I want to get that out there because I'm going to, for a lot of theorems, it's just quicker just to say if and only if. Instead of if this then this and if this then this, just if and only if it goes both ways. Is that cool? So the limit of a sequence is L if and only if for every epsilon greater than 0. Now that would be like the 1/10th and the 100th from earlier, yes? For any number, we call that number epsilon normally, greater than 0. So somebody can come say, I want you to be within 1/10, and I'm like, okay, we'll go out to 10. 100th, okay, we'll go out to 100. So for every number somebody could say, there is an integer n such that when n is greater than n, that is true. Okay, so let me say this in English. You guys ready? We think the limit is L. Like we thought the limit was 2 with that 2 minus 1 over n. Somebody came along and said, oh yeah? Well, I want you to be 1/10 away from the limit. That's what this says down here. The distance between the sequence and the limit is less than, in this case, 1/10, 100th. So the epsilon is the challenge somebody gives me. Oh, you think your limit is 2? I want you to be within 1/10 of 2 forever. So didn't we then find a number n, 10, 100, that then made that happen? So the only way that our sequence can actually have a limit is if for any number somebody gives me, I can find an element designated as a big N, a10, a100, so that forever after that value, I am closer to the limit than what that guy said. If the limit of my sequence is 3, what has to happen eventually? Couldn't my sequence just go crazy for a while? Eventually, what better happen if the limit is 3? Holy shit, oh, what's got to happen over here? Ah! If the limit is 3, I better eventually start getting close to 3, yes? At some point, I must be forever closer than some distance away from 3. If that never happens, then I'm like oscillating. I'm not going to 3. Are you guys not all with me? This is major formalization of the earlier thing we were talking about. How much are you going to have to directly work with this? Not a bunch. That is more than 0, though. Okay. So to kind of follow along with the earlier thing we did, let's see if I can. When an was 2 minus 1 over n, and somebody said epsilon was 1/10, we made n 10, yes? Yes? If I go out to 10, I'm 1/10 away from 2. And then if little n is bigger than 10, I'll always be closer than 1/10, yes? Because then the next one is 2 minus 1/11th. The next one is 2 minus 1/12th. I keep getting closer to 2, don't I? I'm always at most 1/10 away from 2. And then somebody says, oh, okay, 100th. Try that one. We're like, no problem. We'll go out to 100. What else you got? I'm forever closer to that. Forever closer to that. Yeah. Is that okay? it's unfortunate we don't really work with this very much with you. Like my 180 students last semester, I think I had to skip section 2.4, which made me cry a
I
lot.
think so.
Huh? Did I?
think
I did.
so.
My summer class I got through it, but last semester I had to skip it. And that's where we talk about epsilon delta. But I'm like the only teacher left that ever teaches it anyway, to be honest. And everybody's like, yeah, that's why I didn't take you, Jeff. All right, Jeff.
So,
Last semester you would have been fine.
so
I didn't
in a
teach it.
like if we're given a problem like the 2 minus 1 over n, then then like our job is just to find big N.
Yeah, given an epsilon, can you figure out a big N that is forever after that, it's going to be closer than that.
But it's not always going to be like that, I guess, like simple, like
No, it
like
won't.
just taking the
Which is
10.
why we're not going to get very complicated problems, if any of these.
Okay.
Yeah. Okay. Does some part of that discussion make sense? Do you understand the symbols in the proof, or in this definition? Okay. If and only if it's going to come up a few times because it's just really useful. Okay. Oh. If the limit as x goes to infinity of f of x is L. Yes, sir.
One more thing with the first part. What's
Yeah.
what's the difference between the big N and the little n?
Little n goes from 1 to infinity. Big N is a specific value. It's sort of like, do you guys remember the slope formula? What's the slope formula? y2 minus
Y1.
y1. What was the 2? What's the y2? That was a specific y value, yes? So in this case, instead of saying n0 or n1, we just said big N. Big N is a specific little n value. So forever after 10, I'm always going to be closer than 1/10. Is that cool?
Yeah.
So n is a specific value. Little n is everything from 1 to infinity. Okay.
It's just like trying to find like where it wants you to start.
Yeah, at what point does it forever after meet the requirement to be this close? So that's a big N, yeah. All right. So this looks more like what we did in 180, correct? We've gotten back to f of x and so forth. So I'm trying to connect functions with sequence notation because there is a connection. An equals f of n, n an element of the integers. Then the limit as n goes infinity of an equals L. That's kind of silly. This is really silly. Can somebody give me, like for example, couldn't I say f of x equals 2 minus 1 over x? Couldn't you have f of x equal 2 minus 1 over x? Couldn't that be a function that you work with? Isn't an up here just borrowing that function to make sequence elements? It only allows natural number inputs, yes? You guys kind of with me? This is not that big of a deal. You'll see why when we start doing some calculus to our sequence stuff, which we're going to actually do a little bit tonight, I have to go from n to x. Remind me, what does n mean? What could n be? Any natural number, 1, 2, 3, 4, 5, yes? So if I want to do a derivative, technically can I do a derivative of a function that's defined discretely? Because what's a derivative all about? Where does it look like I'm going? Yes? And if you have a discontinuity, can you do a derivative there? No. So isn't dot, isn't that like nothing but discontinuous? So if I want to do calculus to a sequence definition in AN, I have to replace it with x so I can do calculus to it. Because n is not continuous. It's 1, 2, 3. It jumps. Okay. So this just kind of establishes a little baseline connection. All an is it's making a function out of n. So there's a connection between the function it uses and the function that it would have been back in like 180. Okay. Oh, then we get these exciting things. Okay. I'm going to bust through these a little bit quickly, but let me know if I need to slow down. I'm going to tell you that an and bn are sequences. C is a constant. Okay. So an and bn are sequences. So it kind of makes sense. If I have multiple sequences within a problem, I can't call them all an. So we just start doing A, B, C, however many sequences we got. In this case, A and Bn are sequences. C is just a number, some number. What do you think is true for this? What's your gut tell you about this?
That it's the limit of an plus the limit of
Yeah.
bn.
So of course this is borrowing the limit laws from just normal limits of functions from 180. Okay. So most of these are going to be pretty straightforward. What about this guy? Well, let me just do this. What if I put a minus there? It would just have a minus there. Okay, so we're not going to make a separate law for that. What about this then? Well, this is actually what I want. Make that the C. The limit of can. What do you think you can do with C? It's a constant.
Pull it out.
You can pull it out. I like it. What about this here? What do you think? Yes, you can actually take the individual limits and multiply those. Which is actually very useful in a certain homework problem that somebody was asking me about earlier. Let me see. For this one's got one little caveat. This would be the limit as n goes to infinity of an divided by the limit as n goes to infinity of bn. What must be true about bn? Can't be 0, yeah. I like it. Okay, so there's some limit laws. I've got a few more very exciting kind of rules to share with you. This should look somewhat familiar. Can somebody help me interpret what this says? What's true about the sequence Bn? All of its elements are always plus u. Yeah, it's in between An and Cn, right? So if An is 1 and Cn is 3, Bn could be 2 or something in between 1 and 3. Yes. So every element of Bn must be between the associated elements of An and Cn. Yes? Anyone know where I'm going with this? We're talking about limits, and they just set up this inequality. Squeeze theorem.
Oh,
So if this is true, and the limit as n goes to infinity of an equals the limit as n goes to infinity of cn equals L, then the limit as n goes to infinity, Jeff, this is so exciting. What would that have to be? If this goes to L and this goes to L,
then the middle one has to go to
that one's got to go to L, yes? That's what I want to tell you, Jeff, go to L. So, if AN's elements are always less than, and BN and CN's elements are always bigger than. And AN and CN eventually agree somewhere. BN is in the middle. It's got no choice. It's got to be the same thing, right? It's like the hydraulic press at the end of Terminator. It's got no choice. It's got to become smushed. Okay. And then a nifty little other thing. If the limit of the absolute value of a sequence is 0, what must be true about the limit of the sequence itself?
But the limit's 0.
It's got to be 0, yeah. So what kind of a sequence might this apply to most directly? I mean, if the sequence already has nothing but positive terms, this doesn't really mean anything. So what kind of sequence have we seen that this might actually apply most directly to? Alternating series. So if I have an alternating series, so if I have an alternating series and A1 is here and A2 is there and A3 is there and A4 is there and A5 is there and A6 is there and A7 is there. So it's alternating, yes? Maybe this is 0 and it's positive, then it's negative, then it's positive, it's negative, then it's positive, then it is convergent. Well, if I make all the elements positive, now it's going to go like this. It just go to 0 still, yes? Let me try to draw this out. So if I have AN is somehow alternating. So here's A1, A2, A3, A4, A5, A6. So eventually it converges to 0, yes? The absolute value of AN would just make all of these points come up here, yes? And then I would just get, it would just still go to 0, yes? Okay, good. So that, by itself, that little law is kind of silly, but when we start investigating alternating series, which is when I add up alternating sequence elements, this idea is going to become very important. Okay. I love you guys. You've buried your stuff. Here it is. Did I already say that one? Yes. There it is. All right. So, let me say a few more things, and then I've got a little handout for you guys to work on. How many of you guys know what this notation means? Have we talked about this yet? Factorial?
No. We haven't, but.
Okay. Has anyone never seen that in terms of a math process? Like, that is not me saying 7! Right? So, that is actually a mathematical process, just like a square root symbol. It's just that the geniuses that were back in the day, they were like, oh my God, what symbol have we not used? Just put an exclamation mark, like, okay. So square root, when I write that symbol, you know exactly what it's asking you, yes? That's the whole idea. Right now, I've got a symbol, and some of you guys are like, I don't know what the shit that means, man. So here's what it means. It always means the same thing. Start with 7, and then multiply all the way down to 1. This is very, very useful in probability statistics, because this is how you count. If I had 7 people, how many ways could I arrange them? This many ways. How many people can I put in the first spot? 7. For each of those 7, how many people could I put in the next spot? 6. That's 7 times 6 so far. There's the next spot, and that's that. There you go. So factorials show up all over the damn place in probability and statistics. They're combinatorics, combinations, permutations, blah, blah, blah. You don't have to know stats and probability for this. I'm just letting you know, if you take them, you might see them. I want to point out, mathematically, isn't this the same thing as this? That's kind of silly, yes? But I'm going to show you later how this is very important. Either way you do it, what do you get? Well, no.
Oh.
What is it?
Yeah.
5,040.
Yes, there you go. Which is the sum of the first 100 natural numbers is 50/50. Do you guys know that?
Yeah.
Okay. Now, does that make sense? So if I said 5 factorial, could you figure that out very quickly? Okay, now, what the hell is this then?
You multiply all the numbers starting with n down to 1.
Okay, so let's see. N times,
N minus 1.
good, times,
Times n minus 2.
times, where do I stop? 1. Okay. So how long is that list depends on how big n is. I could stop at the first element. If it's 1 factorial, it's equal to 1, yes? Here, while I'm talking about it, what the shit is that?
1.
1.
Can you show me?
Not.
No. So watch this. This is cool.
I don't know.
Watch it. You ready? Watch it.
I
Watch
was
it.
just told that it was really complicated.
No, it's not. Whoever told you that, you gotta go slap. What's 2 factorial?
2 times 1.
2 times 1, 2. Yes?
Yes.
How do I get from here to 1 factorial? Wouldn't I divide by 2?
Yeah.
Yes? So wouldn't this be 1 factorial would be 1? Yes? You with me?
Yes.
So to get from 2 factorial to 1 factorial, I divided by 2. To get from 1 factorial to 0 factorial, I would divide by 1. And just to make sure you really believe me, 3 factorial is what?
1.
3 times 2 times 1, yes?
1.
Which is 6. How do I get from 3 factorial to 2 factorial? Divide by 3, yes?
Uh-huh.
You with me?
Mhm.
So if I do that, then how do I get to 0 factorial? Divide by
1.
1. 0 factorial is 1. And the real idea is, if I had no people, how many ways could I arrange them? 1 way. Not. If you had $0, how many different ways can you arrange them on the floor? 1 way. Empty floor. You guys kind of with me? So that's physically what 0
Very
factorial
sad
means, yes?
situation.
And that's Jeff. Let me roll around my money. I put it down on the floor. Yeah. The anti-Scrooge McDuck. Okay. I was, yeah. I remember my college years, they were lean and mean, and I ate a lot of ramen and cheesy poofs.
Yes.
Okay. I still do,
That
but
is
because I
the
want
life
to,
of
not because I have to.
college.
Now, is that okay? So 0 factorial is officially 1. There are other proofs of it. If you felt that was kind of flimsy, well, damn, that's rough. But you can go look up some other proofs, yes. They can get kind of difficult. But there's not a damn thing wrong with this. This is how I do, like, figuring out what negative exponents mean. Just go with me for a second. 2 squared is 4, yes? How do I get to 2 to the first? Don't I divide by 2? Yes? How do I get to 2 to the 0 power? Don't I divide by 2? So that's kind of like, not a proof, but it shows you what a 0 power does. How do I get to 2 to the negative 1? Don't I divide by 2? So this idea of seeing a pattern and how to get from one to the next, we use that very often in mathematics to understand some concept. Is there a proof about negative powers? Yes. Is that decent enough to see the pattern and to accept what it does? Yes. Okay. So, make sure I'm not doing something I want you guys to do. I sort of do, but I'll do an example with you. What do you guys think about this? N factorial over n plus 1 factorial. Which one has more elements, the top or the bottom? So let's start with the bottom. It's got more elements, correct? In fact, if you start to rewrite the bottom, let's do it the traditional way. We'll start with n plus 1. What would they be multiplied by? N, yes? What's the definition of factorial? Start with the number I'm given, multiply by 1 less than that, multiply by 1 less than that, yes? All right, am I done rewriting n plus 1 factorial? What do I have to do next? Keep going to 1, yes? But what is n times everything down to 1? What is that defined to be? And factorial, so do you see how, bam, yes? I just pluck the first piece out, and then I have n factorial left. That's telling me to keep going, yes? And so how do I simplify this then?
The n factorials.
Die. 1 over n plus 1. So I just killed the repeated parts, yes?
No,
That's how two factorials can interact with each other. Okay. This idea is going to dominate a good chunk of the middle part of chapter 11. You're going to see factorials in your dreams, just to warn you. Okay. So I want to really make sure, does everything we just did right here make complete sense? So for example, if I had 18 factorial, is it okay for me to rewrite it like this? Do those mean the same thing? Yes, because that means multiply down to 1, and this is multiplying down, and that says keep going down to 1. So of course that's good. So if I wanted to do 18 factorial divided by 15 factorial, I can now do 18 times 17 times 16 and be done. Yes? That's the idea that we're using. I like it. I like it a lot. Okay. All right, so I'm almost done talking for a little bit here. Hold on. Let me see if I'm just going to throw this at you. Here's a sequence. Do you think that sequence is increasing or decreasing or neither? What I mean is,
Decreasing.
as you follow it, are the elements getting bigger or smaller or neither? Maybe it's oscillating.
Smaller.
Why?
Because
I keep dividing by bigger stuff. Now, how do I officially show that though? You can do it two different ways.
You can start doing like a to the 1, a to the 2, or not to the, but
So you can never prove something generally about a sequence by looking at a finite number of terms.
oh, is this the thing where it's like
If this is decreasing,
something doing?
if this is decreasing, how must these relate? How must those relate if it's decreasing? How much should one term versus the next term? Which one is bigger? The first term. Because every time, if it's decreasing, the next term should be smaller than the term before, yes? So this should go like this, yes? Is that true? Well, what's AN?
3 over n plus 1.
And what's AN plus 1?
3 over n plus 1 plus 1.
Yes, good. And which one's bigger? The one that's divided by less, yes? So is this decreasing then? Did we just investigate every element of the sequence? Not just a few, but did we investigate every element? Yes, because what's n? Could be anything. So didn't I just look at the 8 millionth element versus the 8 millionth in first? Yes, I did. There's another way to do this if you don't like that. And sometimes this math can get really gross based on what AN is. This is where we do what I was talking about earlier. How in calculus do you show that a function is decreasing? Take the derivative and show that it is negative. Yes? So what's the associated f? What function is AN using to create itself? 3 over x plus 1. Good. So now I can do calculus to it because now I have a continuous function, yes? So what is f prime? And you can write this like this, remember? What's f prime? What's the derivative?
3 natural log.
No, not the integral. The derivative.
Oh,
Come on, guys.
gosh.
Derivative. Yeah, jump on that.
Negative
Derivative. Holy
3
shit.
X
Yes, good.
plus
Negative
1
3. X plus 1
minus
to the
2.
negative 2. Yes. So it'll be negative 3 over x plus 1 squared. Yes. What are the values allowed for x, considering where it came from? What's the lowest x could be?
0, 1.
1. Yes. In this case, it doesn't matter because the bottom is being squared. Yes. So the top is always negative, the bottom is always positive, so f prime is always negative. Decreasing. I need you to see, you have two ways you can do this. If I ask you, is the sequence increasing or decreasing? You can either see the connection between one element and the next, or you can change it to a f of x and take its derivative. However you're feeling at that moment. It'll work either way. I like it. We know decreasing functions and how to do them from calculus. This way gets ugly if the derivative is gross. This way gets ugly if I can't really see the connection when I put n plus 1 in. Okay. And there's one last idea. There's something called bounded. So the easiest sequence that would be a bounded sequence would be something like this. Yes? Is that a bounded sequence? What do you think bounded means? Yes. So you could actually have an upper lower bound, but if I just say bounded, it means it has both a ceiling and a floor. And of course, what's the ceiling and floor of this? 1 and negative 1, yes? I like it. Is this increasing or decreasing? Hmm? Neither. The sucker's oscillating. Sometimes it goes up, sometimes it goes down. Damn little thing. You with me? What do you think if I had a function, an an that was related to f of x? Is that cool for me to say right now? You guys with me? And the function is always increasing, and it also is bounded. If the function is always increasing and it's bounded, I'll call this m just because it's the most. So the function is always going up, but it's also bounded. What do you think it must be true about the sequence that uses that function? It has to converge. Could it oscillate? That would violate what did I say that would violate? That it's always increasing, so it can't oscillate, yes? Can it go to infinity? No, because that would violate the fact that I said it has a bound, yes? So it's always going up, but it has a ceiling. So it has to do, maybe it won't be this clean. Maybe it'll be like, blah, 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 but it's still going to eventually kind of do this. It has to converge then, yes? Okay. I love you guys. Okay. So if it's, and what we call, if it's always, this would work if it had a floor and it was going down the same way, yes? So if it's always increasing or always decreasing, we call that, oh God, the name just went out right of my head. Not monotonic, yet monotonic. I don't know why that didn't make sense to me for a second. I think for a second I was thinking genitonic, but that's not really working here. Monotonic, monotone. This is like my one of my teachers. His name was Dr. Fanning, but he was actually one of the best teachers there. But he talked like this. He'd say, "Today we're going to talk about structures in mathematics," and we're like, "Oh my God, dude, you're so monotone. Please, dear God, you guys go with me. You know the word monotone. You always have this. You know. So monotonic means it's established if it's going down or up, and it just keeps doing that forever. Okay. So if I'm bounded and monotonic, I must converge. I've got no option. I must converge. What's the only way I escape converging? I go to infinity. Bounded doesn't let that. Or I oscillate. Monotonic doesn't allow that. Okay, maybe. So let me do as I promised a while back and shut the hell up. Because you're all like, yeah, the guy was monotonic, but he's not got your crazy voice. So. All right, guys, let's take a look here. Let's take a look here. This guy Very often I'll have a student just focus way too much on the fact that it's sine, and you'll say oscillating, so therefore no, right? What's happening on the inside?
It's getting really small, so it's going to 0.
Yeah, so I can do this. We know this from Calc 1. If I have a continuous function, I can take the limit inside. And of course, what's the limit of that?
0.
Because the bottom just grows crazy and the top stays in pi. And what sign is 0? 0. Good. This one, what's the very first step?
Rewrite log properties.
Yeah, so use the fact that the difference of logs is the log of the quotient. This is a continuous function on its domain. Is that okay for me to say? Is natural log continuous everywhere? No, but it's continuous on its domain. I don't have to pick up my pen to draw a natural log, yes? So if I take that inside, why is this really easy to do? It's just the rational functions, and the degrees are the same, so what's the limit of that stuff on the inside?
With the addition though?
1, and what's the natural log of 1?
People do that with just
0.
addition. I think it might have to be multiplied.
Now, not every answer will be 0.
Cancel like that.
So then number 2, I start you off
Like
nice.
if you have
Factorial is a very single-minded thing, and I
just cancel.
just want to let you know, just in case anybody wants to look this up. There's a more generalized version of factorial that could handle 1/2 factorial.
Squared plus 2.
On the surface, real quick, on the surface, does 1/2 factorial make sense?
Right here.
Because it would be 1/2 times -1/2 times -3/2, and it would never end.
No, this isn't what we're talking
But there's a function above this called the gamma function,
about. This is.
that whose outputs agree with the regular factorial, but then it extends to all kinds of inputs. Okay. Did I have to tell you that? No. But I couldn't stop myself. Okay. So what's 4 factorial? 4 times 3 times 2 times 1?
Okay, that would give you the, okay.
24.
Now,
Now, I really appreciate somebody was asking me if it was legal to do something and it was beautiful. What's the bigger dude on the bottom? So what I can do on the top is do 6 times 5 times
Yeah,
from asymptotes.
yes, which I need to remember all that.
and what's 2 factorial?
I need to, I probably still have
Yeah,
my
2.
limit
2 times 1.
somewhere.
So then what cancels?
Which feels like the one in the front.
Right? And then you get 60. By the way, if you have a calculator, if you hit the math button and you go to probability, you'll see exclamation mark.
Oh, yeah.
Just to let you know. So let me show you.
The only thing I have to remember is
Alright.
not the bars.
So if you hit the math button, go to probability. Factorial. So if I do 4 math probability exclamation, you get your 20. And you can put you can put the entire this whole problem in, and it'll tell you. Okay. Where are there more elements, on the top or the bottom of C? On the top. Can everybody see that? Because it starts at a higher number, so it's got more elements, yes? So I'm going to start with that, because if I go far enough down in its chain, I'll find the bottom, and it'll cancel. Does that make any sense? If I give you numbers, it'll immediately make more sense. If I had 5 factorial over 7 factorial, where are there more numbers? On the bottom. If I write the bottom out, a couple in, and holy crap, Jeff, you're on the edge. I get to 5 factorial, and I can cancel, and I get 1 over 42, yes? It's exactly the same idea. We know variables are numbers. These 2 numbers are 3 apart. You see that? Those are 3 apart. So if I just start with the top and just start writing it, n plus 2, what is factorial? The factorial is the most single-minded thing in the universe. Start with where you got, and then keep multiplying by 1 less forever, yes? So what's 1 less than n plus 2? N plus 1, what's 1 less than that?
N.
And 1 less than that?
And minus
And I gotta keep going, but I don't want to. So the factorial reminds me that I have to keep going, but the nice thing is, I never do because they kill each other. You don't have to multiply that shit out, by the way. Yes? You could if you want to, but. Is that okay?
Cool.
Ooh, it's even higher than okay, it's cool. Now, there are 2 ways to do this. I am hoping, well, let's see. Did anybody try 3a yet? What did you do? Good, so I would highly recommend converting this to the associated function of x and taking its derivative. You actually could throw an n plus 1 in, cube it, square it, distribute, blah, 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 and you could see. I'll show you because I did it just because I was curious how gross it would look. Here. So if you do it, what is this? That's an, yes? And this is an plus 1. Do you see it's an plus 1? And doesn't it have extra positive shit? So isn't an plus 1 bigger than an? I don't want to do it that way. What's the derivative of this?
6 over x squared minus 2x.
What do you have to show? You have to show if this is greater than 0 or less than 0. And of course, what's the smallest value I could use for x, considering it came from a sequence? 1. So how do you determine if this is bigger, if this is positive or negative?
1 for next.
One way to do it is to factor it. For any x greater than or equal to 1, what is this? What kind of number is this? Is it positive or negative? Positive. What kind of number is this for x bigger than or equal to 1? So this is always greater than 0, therefore this sequence is increasing. Okay. So most often derivatives are the way to go. Sometimes it's not the way to go. You want to do the n plus 1 thing. Okay. When? I don't know. Figure it out. No, I mean, if you do a few problems, you'll see. I'm lagging in real life. Oh my God. Okay. This one, obviously, dear God, what do you want to do with this one? I want to pretend like you didn't write it down, Jeff. No. I want to do the derivative. What rule do I have to use to do this guy's derivative?
Chain.
Not chain. Well, sort of chain, yes, but primarily what? Product, yes? Okay. So what's the derivative of negative 2x? Negative 2 times, leave this guy alone. Minus 2x, what's the derivative of e to the negative x? Negative e to the negative x, yes? Is that cool? So this is negative 2 e to the negative x plus 2x e to the negative x. And what am I trying to show?
If it's increasing.
If it's increasing or decreasing. So if I take out a 2 e to the negative x, do you guys see how that's x minus 1?
Mm-hmm.
Now if x is 1, what is this actually?
0.
0. But for everything after that, what is this? No. Oh, I see what you mean. You don't mean 1. You mean positive. Okay. You guys see that? So this is increasing because the only thing it's not positive for is the first term, and who cares? That's just what gets us started. Yes? In general, if the first finite number of terms are going crazy, but then forever after some term it's going up or down, I would call that an increasing or a decreasing function. Because all that matters is what's happening in the long term. So this one is greater than 0 for x greater than 1. So this sequence is basically always increasing because it's only flat at the first element. Maybe? because the slope is positive, okay? How you guys feel? So we got decreasing, increasing, which means the same thing it did in 180, derivative. We do have another way we can do it, which is investigate the difference between an and an plus 1. That is very often not the best way to go, but on some occasions it's actually better because derivatives get gross sometimes. Yes?
Can you explain how you got like the positives for the first one?
Oh,
No, but yeah.
oh,
How did,
all right. For x greater than or equal to 1, what's true about this number? Is it positive or negative?
positive?
Positive. What's true about this number?
It would also be positive.
So what's true about this number? Because it's made of two positive numbers multiplying, it's positive. Yep.
Okay, so then do you always use x greater than or equal to 1?
Because our sequences start at 1.
Okay.
So it doesn't matter what happens for x is 0 or less because our sequences start at 1. Yes? Okay. Like it. You would, Jeff? Okay. So I just want to say a little bit about, if there's no questions from this handout. So we got the idea of bounded, we got the idea of monotonic, which relates to increasing, decreasing, yes? We have how to, something we talked about last time, but we kind of solidified today was how to tell if a sequence is converging, right? If I have a sequence that is bounded and monotonic, it must converge. Yes? Okay, I like it. So, what we're about to get into is a remarkably important section. But what I want to focus on tonight is I want to make sure everybody remembers this symbol and what it means. And that would be this symbol. So let me just give us a problem and see how we feel about it.
So this is the start of 11.2.
Yeah, so 11.1 set up the idea of how to generate a list of numbers that go forever, yes? 11.2 says, oh, that's good. What if you take all that stuff you did and add them all up? The question will now become, when does that sum converge? Now, on one level, I'm almost certain some of you guys are in here going, we're just playing with shit. We're gonna get to a point where we're gonna do some shit that blows your mind. We're gonna look back at stuff we've done earlier, and some stuff we're gonna develop in this chapter are gonna make earlier stuff we did so much easier. One of my favorite shirts has e to the I pi plus 1 equals 0. This is a true equation. E to the I pi plus 1 equals 0. Has anyone ever seen that before? Well, if you've had me for class, I've worn the shirt.
Yeah, I've seen the shirt.
This does not make immediate sense. This I, by the way, is the complex number I. So what the shit does e to a complex number mean? I don't know. We're going to learn later this semester. This formula, math people geek out about because it has the additive inverse, it's got the multiplicative inverse, it's got pi, it's got complex number, and it's got e. All at one time. Holy shit. So math people see this and go, oh. They go just like that. Okay, I'll stop. I'm sorry. So later semester. So what we're doing is we're building up the stuff, the basic skills we have to have in order to get to the level where we can prove that, for example. Not just that. That's not our end goal. It's going to be a little side note. Oh, look, we can prove that. And just to give you a little extra impetus of motivation, do you guys know anything about this integral?
Oh, it's not possible.
Not possible.
You have to
That
do
is
the,
impossible. You cannot integrate this. You can't. But in chapter 11, we're going to integrate that. Somehow those two statements are true, and you'll see why. So tell me real quick, why is this not really a full series? Because it doesn't go to infinity. So this is kind of like a partial sum, potentially, yes? But did anybody do this yet? How does this work?
Don't you have to take the derivative?
Nope. This is kind of like function notation again, right? Isn't the inside a function of I? And what are the limits of the sum tell me?
One
I
to
can be
1 to 3.
1, 2, 3. So it's got in it a sequence generating piece, yes? But the symbol E, we chose it because that's a Greek letter S, and it means sum. So the math people of old, they're like, well, let's use the letter S. Let's make it Greek, okay. So then we use the letter S for sum. So when I plug a 1 in, I get 0. When I plug a 2 in, I get 2. And when I plug a 3 in, I get 6. So then this sum is 8. Amazing. Okay, I like it. So you guys might remember some of the formulas from last semester. You guys remember this at all? Does it look at all like vaguely familiar to anybody?
Yeah.
If you took me, it does. Or it could, I should say. But I feel like some teachers might have skipped this, which makes me really, really cry inside. Because this is really important. This is section 5.2, I think. And this was when we were connecting, adding up rectangles, because that's where we used that symbol last semester, or whatever semester you took calculus. We used that symbol for summing up rectangles. Then we increased the resolution to infinity, didn't we? We used infinite rectangles, which made it perfectly line up. Not do this stupid little, oh, I went over, I'm so sorry. No, we made it fit perfectly, because we used infinite number of them. And then we just took the letter S and made it long, and that's the integral symbol. Ooh, look at us. It's an infinite sum, so let's make it a long S. Okay, you guys kind of with me? That is really what happened. Did you guys all know that? The integral symbol is just the letter S long. Why? Because it's an infinite sum. Okay. I love you guys. So I'm really sorry if you didn't do as much of this as you should have, because we're going to use the shit out of this. Chapter 11 is going to be ruled by this. Yes? So I will take time to show you some of the way this works algebraically, because you need to be able to do that. Okay. Right now, I just want us to understand the basics of how this thing works. Just the real basics. And it looks like we all get it, maybe. This one right here is just a formula that hopefully some of you guys proved. It's Gauss. There's actually a urban legend. And who doesn't know this? Does anybody tell me honestly? You feel like you've never seen this before? Anybody? Yes. Okay. If you have, just sit there for a minute. What does this actually say? Can somebody tell me? In fact, let me start this at 1 because 0 doesn't really make sense. What does this actually? How does this translate into a list of numbers I'm adding up? What is I at first? 1. The symbol means add. What is it now? 2. And I'm going to do that up to n. Is that cool that I did that? If I'm going up to n, that means I have to go through n minus 2, n minus 1. Is that cool? Now, here's the trick. So the urban legend is Gauss's teacher, Friedrich Gauss, by the way, Friedrich Gauss. His teacher was trying to, and the students were going insane. He's like, oh God, shut it. Everybody, you must add up the numbers 1 through 100. And if you don't do it, you can't do anything else. You must do that. So everybody's, oh man. And they start doing it. And the teacher sits back and says, I can read my book now. I'll just read my book. It's going to take him forever. And Gauss comes up and says, I know, I got the answer. It's like, God damn. So Gauss got the right answer in like 11 seconds. Good for him, right? So what the shit did Gauss do? He didn't do 1 plus 2 is 3 plus 3 is 6. That would take for freaking ever, yes? I'm only up to 3, and that's holy shit, I got up to 100, yeah? So what Gauss did was, what's 1 plus n?
N.
N plus-
N plus
What's 2 plus n minus 1? What's 3 plus n minus 2? Right? How many pairs? Every pair of numbers, if I do that, add up to n plus 1. How many pairs will I have? If I had 100 numbers, I would have 50 pairs, yes? So obviously, however many numbers I have, I cut it in half. So how many pairs of numbers are there? N over 2. And every pair sums up to n plus 1. So if I rewrite that a little bit, I get the sum of this. So if I want to add up to 100, what would that be? It would be 101 times 50, which is 50-50. So the sum of the first 100 whole numbers, or natural numbers, is 50-50. I should say natural numbers. You guys semi with me? Okay, so that is something you should have seen and discussed in Calc 1. And if they didn't, a pox on them. Okay. It's no good. All right. So, let me talk about one last thing and then I'll let us out of here. I just want to solidify something that we were talking about earlier. If I do this, all right, so already this seems like it's going to be horrendous, yes?
Mhm.
But if I do this,
It's gonna go to 0.
well, okay, now this is huge. This is big. I can talk about if a sequence converges. That is stupid easy, because all I have to do is take the limit and see if it approaches a number. You with me? I need this to make sense. Do you all agree the limit of the sequence that I have inside that sum is 0? I don't have a clue. If that's all I know, the series can converge or diverge. I have no idea. No idea. If, I really want you with me on this. If I had a sum where the thing inside, like what is this? What is the limit of the sequence inside that sum?
It's a.
Let me make the bottom +3 so I don't get some weird infinite thing going on.
It's a.
What's the limit of the sequence inside?
It's
1, yes, it's a ratio of two
Yeah.
polynomials where the degrees are the same, so it's a coefficient, blah, 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 okay. Doesn't that sequence eventually become basically just 1, 1, 1, 1, 1? Isn't that what that means? I need you to understand that that's what that means. If the limit of that is 1, it eventually becomes basically 1, 1, 1. Not 1, maybe 0.9999999999999999999999999999999999999. For most humans, that's freaking 1. You with me? And if I add up 1 forever, what do I get? I get freaking infinity. Of course I do. That's the most basic definition of infinity is start with 1 and add 1 and keep doing that. That's infinity. That's why it's not a number, it's a process. If the limit of the sequence I'm adding is not 0, it's got no chance to converge. Does that make sense? Because eventually, the numbers become basically that number, and if I add up an infinite number, I don't care. What about this? What's the limit of the sequence inside here? What you got, Jeff? 1 over 1,000. The degrees are equal. So as I let n go to infinity, it's the ratio of the leading coefficients, yes? Let ratios of powers of n be easy as shit to do the limit of, yes? 1 over 1,000, is that a very big number? No. But if I add 1 over 1,000 up an infinite number of times, I'm going to go to infinity. If I add 1 billion zeros onto 2,000, the limit will not be 0, correct? Will the limit be a very big number? No. But if I add it to itself forever, it's going to infinity. So the minute the limit of the sequence in the series is not 0, the series cannot converge. It must diverge. Are you guys with me? So when I ask you, does the series converge? What is the first damn thing you're going to do? Take the freaking limit. If it isn't 0, you're done. Do you understand that? So this is really good to know. What's the first thing you do? So if I ask you to integrate something, you rule out u sub. If I ask you to tell me the series converges diverges, you rule out that it automatically diverges. Are you with me? So in those two cases, the answer is easy. Because the limit of each of their sequences is not 0. So they both diverge. Are you guys with me? They can't possibly converge. So in order to maybe converge, what must your limit be? The only way you could possibly converge is if your sequence elements goes to 0. It's all about then if it goes to 0 fast enough. So real quick, just to kind of show you something a little ahead of time. If I had this sequence, this series, the sequence is 1 over n, that diverges. Because it doesn't get out of its own way fast enough. It's 1, 1/2, 1/3, 1/4. That's pretty small already, but if I keep going that forever, it actually adds to infinity. Or approaches infinity when you add these elements. This one converges. Both of these have a limit of what? What's their limits? 0. So they both have a chance to converge. So what is the suckiest thing? And by the way, this class is the one who I love this. I love this shit so much. So when I say suckiest, I don't really mean it. But what is the worst thing that would happen to us as students is if the limit of the thing inside the series is not 0. Is 0. If it was not 0, I'm done. If it is 0, all of my work has just started. Because now I've got to figure out, it might converge. So then we're going to develop a lot of tests that we can apply to see if it's going to converge. So a big chunk of chapter 11 is, if the limit is 0, how can I tell then? Does it converge, get out of its own way fast enough, or does it not? Yes? Okay. So looking back at this guy. Can somebody tell me a few elements of this? 1/10?
100, 1,000,
Now real quick, what's that as a decimal?
0.1.
Isn't this the thing I keep using? Can somebody tell me the limit? I'm sorry, can somebody tell me the sum? Not the limit, but the sum. What does that sum up to be? 0.11111, which I told you is 1/9, yes. If you don't believe me, what's 0.333 forever? You know this. 1/3. Divide that by 3. Don't you get 0.1111? And what's 1/3 divided by 3? 1/9. So 0.1111 is 1/9. 0.2222 is 2/9. Okay. Is every sum going to be that easy? Oh, hell no. But that's a good example of a sum, a series, that converges. And what told us it had a chance to converge? The limit of this is 0. So if the limit is 0, your work has just started. If the limit is not 0, you're done. If the question is, does this converge or diverge? You're kind of hoping for a non-zero limit, because then you're done. Does everybody get that? If the limit isn't 0, it's just going to keep getting bigger. And if how small it gets, if it never gets to 0, it's just going to keep getting bigger. It's going to go to infinity. Okay. All right. That's enough. That's enough. So it's kind of an overview. So next time we'll get into 11.2 proper. Have a really good weekend. We all deserve a good weekend. It's been a rough week. I'll see you guys. next week. Does it survive? It did.